All right, so this unit is going to be on concavity, the section. So concavity is kind of, we should talk about a little bit what concavity is in general before we get into anything crazy with it. So maybe just so you understand what concavity is. So when something is like this, it's concave down, because if you think about like rain coming down on it, right? Imagine this is rain, okay? It's not going to hold water. If the water runs off, it's concave down. So anything that's like looking like that is concave down. However, anything that's looking like this, so this is concave down, anything that's looking like this is concave up. Okay, concave up. So then the question becomes, if we look at a graph like this, right, where does it change from concave down to concave up? Where it is concave down here, we can say, right? And it's still concave down this whole time, right? And we're kind of like looking in this area. It looks like it's still concave down, concave down. But where does it change? Because right and around here, something happens. And that's called a point of inflection. This is concave up for this section. So if you look at that, you can kind of see something happens there. We don't know exactly what's happening there. But if we study the derivative and the second derivative, we can kind of understand what's going on there. So that's what we're talking about today, concavity and the second derivative test. So at least we understand what concavity is, in case you have forgotten from pre-calc. So let's look at the definition here. So it's concave up. So basically the graph of f, which is the original, right? The original is concave up if f prime is increasing. Well, this is what I want to say. Like if we think about this for a second, and f prime is increasing, well, what does f prime is increasing mean? F prime is increasing means what? If a function is increasing, what do you know about the derivative of the function? F prime is increasing, it's going up. It's going like this, right? It's going up. So we're just looking at a bunch of increasing functions. See those lines? Well, what can you tell me about the slope of those lines? They're positive, right? So that means that f double prime is positive. Okay, that's what we're looking at. And of course the reverse is true. It's concave down. The graph, the original is concave down if the derivative is decreasing. Therefore, f double prime is negative, which implies, right, f prime is decreasing. Okay, well, let's just talk about that for a second. There's going to be some weird stuff going on here, but I want to show you something before we get into this example. So here's the first thing. This is a little bit off of what we were going to do, but I think we're in pretty good shape here. So let's look at this. Let's look at this graph right here, and we can all agree that it's concave down, agree? So we know it's concave down, and let's just put in a bunch of like slopes. So I just want to analyze these slopes. Okay, so now let's just talk about some numbers. Like a number for this slope, it looks like this slope here is pitched pretty high. I'm going to say the m there, the derivative, the slope of the tangent line, the slope of that is going to be around, I don't know, 10. And then this slope is a little bit less, so maybe this slope is 8. And I'm making these up. This slope might be like 5. This looks like it has a slope of about 1. This looks like it has a slope of 1/2. This looks like it has a slope of 1/4. This is actually, over here is a negative slope, right? So that might be like a negative 1/4 slope. This is like a negative 1/2 slope. This is like a negative 1 slope. So if we just kind of like look at all these slopes, right, and we just kind of go in this order, 10, 8, 5, 1, 1/2. What do you notice about those numbers, like as we go this way? 10, 8, 5, 1, 1/2. They're going down, aren't they? And then 1/2 to 1/4. 1/4 to negative 1/4, negative 1/2, negative 1, probably negative 5 soon. These numbers are going down. So what I'm saying is the slopes, which is the green lines, right, are decreasing. They're going down as time goes on. Now this illustration might not make a ton of sense to you, but if you can get to a point where you understand that the slopes of these start out really positive, then they go to 0. So they start out really positive, then they become 0, and then they start going negative. I mean, these slopes are going down. So if the slopes continue to decrease, then we know that the second derivative of this is negative, because the derivatives are decreasing. So if the derivative is decreasing, the second derivative is negative. So this is concave down, second derivative is negative. Let's get into some more concrete examples. Feel free to look that over and understand it at some other time, but here is an example here, and we can look at where this is concave up and concave down, but before we do that, let's just try to analyze this problem right here. So let's make that a little bit bigger and start going for it. So we obviously need the derivative, which is going to be 3 1/3, right, x squared minus 1, so just x squared minus 1. That's f prime of x. And we're going to need the second derivative at some point, so we might as well just get it now. Okay, so we found the second derivative. And we want to know when the second derivative is positive or when the second derivative is negative. So we're going to go back and make the same number line that we have been doing, but I'm going to put 2 tick marks because this is the second derivative we're talking about. And I'm going to look at the zeros of the second derivative because I want to know when is the second derivative positive, when is the second derivative negative. If the second derivative is positive, that means that the slopes are increasing and that the graph is concave up. Concave up will hold water. So this is here, positive, f double prime is positive, which is concave up, which is f is concave up. Okay, so f is concave, up, and f double prime is positive, and f is increasing. F prime is increasing, sorry. So let's look at the number that's of interest. Well, if this is equal to 0, we have x equal to 0. This is a possible point of inflection. It's not necessarily a point of inflection, but it could be that point where the graph changes from concave up to concave down. Let's look back here. This right here is a point of inflection, POI. So this is actually, here we know it's concave down. That means y double prime is negative, right? And here it's concave up. That means y double prime is positive. Well, here it's at the point of inflection, it's not positive or negative. So we want to see what's going on with our second derivative over here, maybe when the negative 1 or the 1 is happening. And what are we going to plug into? Y double prime. So I go back to y double prime, and I see y double prime, when I put in negative 1, is negative 2. That means that this whole interval is negative. We have a 0 here. And then y double prime of 1 is going to be 2, so this whole thing is positive. So the question then becomes, what does the negative and what does the positive mean? Well, here's the deal. Y is concave down on negative infinity to 0, and concave up on 0 to infinity. So that is what we're looking at. Okay. So these are intervals of concavity and concave up and concave down. So let's just take that answer and let's see why here. Okay. So we see this right here, concave down because of the negative sign from negative infinity all the way until 0. Right. Here's the 0 value right there. I'm making it a little bit messy, but we'll get rid of that. And then concave up from there on out. So the deal is, let's take this answer down and see what it kind of does for us when we look at the graph, the original graph. Grab that, move it down. Okay. All right. All right, so now we have all of this data, and let's see what it means on the graph. Well, look at the graph. Would you say that the graph on this interval, negative infinity, right, until 0, would the graph hold water, would the water run off? It would run off. It's concave down. And then if you look right here, it looks like all of a sudden something's happened from 0 to infinity. It seems like something's happened right there, and the graph would now fill up with water. So this is concave up. And this is concave down. And is there a point of inflection? Yes. There is a point of inflection. And what is that actual point? It's 0, 0. If you look at the original graph, right, the original y graph, we know that if we go up there and we plug in 0 here, f at 0, the function at 0 is equal to 0. So the point of inflection is actually 0, comma 0. And why is that? Since y double prime changes sign. That's why. So that is kind of what we're getting at here. So that's kind of what we want to talk about. Here's possible point of inflection and what it kind of means. Let's just take a break. I'm going to make another video, probably a very short one.